Okay. With that in mind, I have the honor of introducing our speaker for today. Avec tout ça en tête, j'ai le plaisir et l'honneur de présenter notre présentatrice, en effet, notre oratrice aujourd'hui. Elle s'appelle Abigail Dalton. Elle est doctorante sous la direction du Dr Luke Copland et du Dr Wesley Van Wychen. Ses recherches visent à déterminer les processus qui contrôlent la production d'icebergs par les glaciers d'eau des marées sur le champ de glace de Prince de Galles au sud-est de l'île de l'Esmer. Ces travaux permettront également de réaliser une étude complète des caractéristiques des icebergs et de leur dérive dans les eaux canadiennes et d'identifier les risques potentiels liés aux dangers glaciers pour les navires opérant dans l'Arctique de l'Est canadien. So I'm really excited to introduce you guys to Abigail Dalton. She is a PhD candidate at the University of Ottawa, co-supervised by Dr. Luke Copland and Dr. Wesley Van Wychen. Her research aims to determine the processes controlling iceberg production from tidewater glaciers on the Prince of Wales Icefield in southeast Ellesmere Island. Her work also provides a comprehensive survey of iceberg characteristics and drift in Canadian waters and identifies potential risks associated with glacial hazards for vessels operating in the East Canadian Arctic. All of this to say, whoa, her research is cold. Tout ça pour dire que la recherche est cool. Voilà, regarde ma vidéo. So, un petit point linguistique. La présentation se passerait uniquement en anglais. Cependant, vous avez le droit de poser des questions en français. Je serai heureux de fournir la traduction si vous avez besoin d'interagir en français. So just a quick linguistic note, the presentation will be happening in English, but if you do wish to ask questions in French, you absolutely can. I will be happy to sort of facilitate that multilinguistic interaction. So with all of that in mind, I hand it over to you, Abigail. Avec tout ça en tête, je vous donne la parole, Abigail.
Thank you very much. I'm assuming everyone can hear me and see my video.
Oui.
Okay, perfect. Okay, so I will go ahead and get started. So like Trick said, I'm a PhD student in the Department of Geography, and I'll be talking today about the work that I've been doing for my PhD on glacier velocities for the Prince of Wales Icefield on Southeast Ellesmere Island from 2009 to 2019. And just a note on this photo, this is the terminus of Trinity Glacier on Southeast Ellesmere Island, and this is one of the glaciers that I will be talking about during my presentation. So without further ado, I'll start off by providing a bit of background on my study site. So the Canadian Arctic Archipelago, or CAA, contains the largest area of glacier ice outside of the Greenland and Antarctic ice sheets. The CAA is drained largely by tidewater glaciers, which are glaciers that terminate into the ocean. Mass is lost from tidewater glaciers through both surface and basal melting, as well as solid ice discharge in the form of iceberg calving. So glacier motion varies on seasonal and interannual scales. Tidewater glaciers typically advance in the winter and early spring when temperatures are low and sea ice is present at the terminus. Lower temperatures allow for the glacier terminus to thicken, and sea ice at the terminus acts as a barrier to stabilize the calving front. In the late spring and summer, as temperatures increase and sea ice breaks out, calving rates increase. Surface melt and runoff also increase, and most glaciers undergo a velocity increase as a result of that. The relationship between surface melt, glacier motion, and mass loss is complex. So basal sliding is an important mechanism which allows glaciers to flow by overcoming resistive forces at the bed. So water from the surface, as a result of surface melting, makes its way through the glacier to the bed and can act as a lubricant, allowing the ice to accelerate. In some cases, water at the base of the glacier reduces effective basal pressure and allows the glacier to flow faster, leading to increased longitudinal strain or stretching of the glacier, causing crevassing and further thinning. When a tidewater glacier thins enough through melt or this longitudinal strain, the terminus can reach flotation and become buoyant, eliminating basal drag and allowing the glacier to accelerate further. So on the other hand, some studies argue that an increased surface melt will eventually lead to a slowdown in glacier motion over the long term, as subglacial drainage becomes more efficient and water is moved away from the base of the glacier quickly, resulting in a deceleration. But going back to this idea of thinning, so when a glacier is grounded below sea level, thinning of the terminus and intrusion of warm ocean water at the base of the glacier towards the grounding line can create a feedback system where calving and retreat increases, and this is called dynamic thinning. So that's what's pictured in this figure here. So as I mentioned in the last slide, the thinning of the termini of tidewater glaciers can be influenced by increasing air or ocean temperatures, and it can also be triggered by a retreat from a stabilizing pinning point, which reduces backstress on the glacier. So sometimes a glacier is grounded on, say, like an underwater ridge, like a shallow point. And that then increases the buoyancy of the terminus, reducing effective pressure at the bed. And again, as I mentioned before, the glacier is then able to flow faster. It leads to more strain and make the glacier thinner, becomes more heavily crevassed as it flows faster. And then thinner and more heavily crevassed ice is then delivered to the terminus of the glacier where it can more easily calve. And so this creates this cycle. And so this cycle of thinning can retreat can continue kind of as long as the glacier is grounded below sea level and can be influenced by the ocean. And it will only stop once it reaches maybe another one of those stabilizing points, like a pinning point or the grounding line. And this type of rapid retreat and acceleration is something that has been seen in Greenland before on Jakobshavn Glacier, which you may have heard of, which led to the collapse of that glacier over the last couple decades. So moving now to my area of interest, the Prince of Wales Icefield on southeast Ellesmere Island. So since 2000, Trinity and Wykeham glaciers, which are located on the more southern portion of the Prince of Wales Icefield, have consistently accelerated, and they are currently the fastest flowing glaciers in the Canadian Arctic. As of 2019, Trinity flows at a rate during winter of about 1,200 meters per year, and Wykeham at a rate of about 800 meters per year. So along with Ekblaw and Cadigan glaciers, which are located more to the north, these four glaciers currently account for about 83% of the total ice discharge from the Prince of Wales Icefield. So, and to put that into perspective, these four glaciers are responsible for about 58% of total ice discharge from all of the Queen Elizabeth Islands, so Ellesmere Island, Devon Island, and Axel Heiberg Island, which I showed in my first slide. In addition, all four glaciers have undergone terminus retreat since the 1950s. So why is this important? Why do we care? So as you can see in this figure, these changes in the Canadian Arctic archipelago are occurring pretty quickly within the last couple decades. And this can help us to better understand how the CAA glaciers are responding to a warming climate. So for example, over the last 2 decades, northern Canadian Arctic archipelago glaciers have lost mass at a rate of about 28 gigatons per year, and the southern glaciers from the southern Canadian Arctic about 22 gigatons per year. And in terms of human impact, since 1971, the Canadian Arctic has contributed about 3.2 millimeters to global sea level rise. And in terms of solid ice discharge, increased iceberg discharge from the Canadian glaciers poses a potential threat to shipping in the Canadian Arctic and along the east coast of Canada as the icebergs drift south. So as of 2020, the northern Canadian Arctic archipelago discharges about 3.2 gigatons per year of solid ice or icebergs. So this brings me to my research. So past studies have looked at velocity patterns of these four glaciers, Trinity, Wykeham, Ekblaw, and Cadigan, over the last 20 years, but they really only look at interannual changes or changes between years. My research aims to look at intra-annual glacier velocity changes and better understand the seasonality of glacier flow, or how glacier flow is changing within 1 year, as well as over this longer, about 10-year time period. And because these four glaciers are the main iceberg producing glaciers from the Prince of Wales Icefield and some of the top iceberg producing glaciers for the entire Canadian Arctic, I'm also interested in looking at how velocity variations are related to glacier geometry. So factors such as bed topography, ice thickness, and terminus position, and determining how that impacts glacier flow. So I was able to measure these changes using remote sensing methods. So this study used the RadarSat-2 synthetic aperture radar, or SAR, imagery. So that's RadarSat-2 satellite. It was launched in 2007. So I used imagery from 2009 to 2019 to derive velocities of all the glaciers, or of those 4 glaciers within the Prince of Wales Icefield. And I'll get into a little bit more detail about how I did this in the next slide. But for now, I'll just give a little bit of background on SAR imagery. So SAR is a type of active microwave remote sensing. It emits energy, which then interacts with the ground surface. The phase and amplitude of energy received back at the sensor is called backscatter. And the amount of backscatter that's received at the sensor is largely dependent on surface characteristics, such as surface water content and roughness. So for example, a rough surface such as freshly calved ice appears bright due to high amounts of scattering. But a smooth surface such as open water or a glacier surface during the melt season when there's water on top of ice appears darker due to specular reflectance. So this variation in the brightness of the backscatter is called speckle, and it can be used in a technique called speckle tracking. So I was able to measure glacier motion using speckle tracking. So this applies a cross-correlation algorithm to SAR image pairs to identify displacement. So I'll break this down a little bit. So this method starts with 2 winter scenes of SAR imagery. So in this case, from the Canadian satellite RadarSat-2, it was in fine beam mode, which is about 8-meter resolution. And it's useful to use winter scenes because SAR imagery relies on the backscatter. And like I mentioned, it's influenced by roughness and also surface moisture. So in the summer, the melt kind of interferes with the backscatter and it's difficult to get a good return and therefore determine glacier flow. So it's better to use winter imagery. So these image pairs are all 24 days apart, which is reflective of the repeat orbit time between RadarSat images. So this 24-day separation allows for enough motion to occur during this period that there's a detectable difference between the 2 scenes, but it's short enough so that surface coherence is maintained. So I apply this cross-correlation algorithm and to identify the displacement between these 2 scenes, and it outputs a vector file where each vector shows the direction and magnitude of flow over the ice field. So you can see in this image the terminus of Trinity Glacier. So the terminus, and the arrows are following the direction of flow on the glacier trunk. So they're flowing towards the terminus. So this vector file can then be interpolated into a raster, which shows a more continuous image of glacier flow. So I applied this speckle tracking method to 168 pairs of images and then extracted all the velocity values along a center line that I drew on the glacier to get an idea of how flow changes from the terminus up glacier along the center. So like I said, I used the speckle tracking method to derive velocities from the 4 largest basins on the Prince of Wales Icefield, which I mentioned earlier. So Wykeham and Trinity Glacier, which are here further south, and then Cadigan Glacier and Ekblaw over the period 2009 to 2019. And again, this map is showing all the center lines that I drew along the trunks of each glacier, and that's where I extracted the velocity data, which I will show you in the upcoming slides. So getting into the results, moving from south to north, so starting with Wykeham Glacier. I'll break down this figure on the left for you. So along the x-axis is the distance from the terminus, so 0 being the terminus and 40 being 40 kilometers up glacier. And then along the y-axis are all of the image pair results from the speckle tracking, which show glacier velocity from 2009 to 2019. And to clarify what it means by season, so these are showing winter velocities. So it's going from about January to March for each year. So as you can see, there's an overall consistent acceleration from 2009 to 2019 from about 1 meter per day of glacier motion to about 2.2 meters per day. And that's focused in the lowermost 10 kilometers nearest to the terminus. And since about 2015, higher velocities have been extending up glacier. So into that sort of 10 to 15 kilometer range. And what this figure on the bottom right is showing is 3D tomography data, which was collected from a NASA Operation Icebridge flight, which flew in the Canadian Arctic in 2014. And it's measured the bed elevation below each of the glaciers in this study, among others. So what this figure is showing is that about 30 kilometers up glacier, I'm not sure if you can see my mouse, but that's about here, that Wykeham Glacier is grounded below sea level up until that point. So now looking at Trinity Glacier, we're seeing a similar pattern. So there's been an overall acceleration from 2009 to 2019 from about 2 meters per day to about 3 meters per day in the lowermost 10 to 15 kilometers. And with Trinity Glacier, there appears to be periods of seasonal acceleration. So if you look at the year winter 2012, you can see the progression within one season, moving from sort of the lighter yellow colors to the darker red color. But then there's also periods of multi-year acceleration. So from 2009 to 2012, you can see that same sort of progression. You can see it again from 2013 to 2017, and again, even 2017 to 2019. You can also see in 2013 and 2017, those years started off a bit slower and then increased in velocity. So it seems to go through these sort of periods of multi-year acceleration. And also similar to Wykeham Glacier, there's been these elevated velocities that are extending up glacier about 30 kilometers since about 2015 or so. So faster flowing ice, we're seeing it about 20 to 30 kilometers up glacier where it previously wasn't there in the 5 or so years before. And then finally, looking at the bed elevation data in the bottom right corner, Trinity Glacier is grounded below sea level about 40 kilometers up glacier. So about right around that second band. And moving north to Cadigan Glacier. So we're seeing a bit of a different pattern from Trinity and Wykeham glaciers in terms of velocities. So there's clear multi-year variations in flow. So there was a velocity decrease from about 2010 to 2017, followed by an increase from about 2017 to present. And those highest velocities are concentrated in the near terminus area. And we can see that when there's faster flow in the near terminus, that the higher velocities are also extending up glacier. So where they were focused in sort of the lower 10 to 15 or sort of 10 kilometers, they're now extending in the last couple of years up about 20 kilometers up glacier. That said, if you look at the scale, you can see how much faster Trinity and Wykeham glaciers are flowing compared to Cadigan Glacier. So Trinity and Wykeham are flowing at about 2 to 3 meters per day, whereas Cadogan and Ekblaw, which is the glacier I'll show you next, are flowing less than 1 meter per day. So a bit slower. But we're still seeing these interesting patterns. And then looking at the 3D tomography data, again, we can see that Cadigan Glacier is grounded below sea level about 50 kilometers up glacier. So quite far. And lastly, looking at Ekblaw Glacier, we're seeing a similar pattern to Cadogan. So there's these multi-year variations in flow. So we see a decrease in velocity between 2010 and 2015, followed by a velocity increase from about 2016 to 2019. And again, similar to Cadogan, those highest velocities are concentrated really in the very near terminus area, less than sort of the 5 kilometer area. But elevated velocities have been extending up glacier since about 2017, which you can see here. So again, looking at the 3D tomography data, Ekblaw, like the other 3 glaciers, is grounded below sea level about 40 kilometers up glacier. And it's quite deep at the terminus. It's grounded about 350 meters below sea level right at the terminus. So those results showed glacier velocities for winter. And so I wanted to compare how summer velocities, or look at the summer velocities and compare how different they are from the winter velocities to see if there was that much of a difference in flow speed for each glacier. So to do this, I used NASA It's Live data. So ITSLive stands for the Intermission Time Series of Land Ice Velocity and Elevation, and provides a record of land ice velocity for all major glaciated regions using Landsat imagery. So regional velocity mosaics are created by averaging all the available image pairs for any given year, and they're available in 120 meter and 240 meter resolution. So I use these regional annual composites to kind of capture the summer velocities that I wasn't getting through the winter scenes. So capturing that faster flow that we would expect in summer. And so I wanted to use those to compare to my winter data. And this ITSLive data is available openly to download at this website here from the NSIDC, the National Snow and Ice Data Center. So next I'll show you the results comparing my winter velocities with these summer velocities. So again, breaking down this figure, you have the distance along the terminus on the x-axis and then the season on the y-axis. And I have side by side my averaged winter velocity for each season compared to the annual average annual velocity from the ITSLive data side by side. So again, we're seeing an overall acceleration in velocity from about 300 meters per year to 800 meters per year for Wykeham Glacier in the lowermost 10 kilometers or so. And what's interesting is that since 2015 or so, 2014, 2015, we're seeing a similar pattern throughout the entire year, winter and summer, of these higher velocities extending up glacier to about 20 or so kilometers up glacier. And also interesting to note is that since about 2014, there's less of a difference between summer and winter velocities. So as I mentioned in the beginning, glaciers typically flow slower in the winter and faster in the summer. But with Wykeham Glacier, we're seeing less of a difference, especially in those regions higher up. There's less of a difference in the summer and winter of flow. So moving on to Trinity Glacier, we're seeing a similar pattern. So an overall acceleration from 2009 to 2019, so about 700 meters per year to about 1,400 meters per year during the summer in the lowermost 10 or 15 kilometers of the glacier. And again, those elevated velocities are extending up glacier and have been since about 2017 in both winter and summer. And from about 2015 to present, there's again less of a difference between summer and winter velocities. So it's much clearer here with Trinity Glacier. From about 2009 to 2013, you can really see a difference in color between the winter and the summer velocities. So it's flowing slower in the winter than it is in the summer. But around 2014, 2015 or so, there's much less of a difference. So meaning that Trinity Glacier appears to be flowing just about as fast in the winter as it is in the summer in these last 5 years. So moving north to Cadigan Glacier, we're seeing a different pattern here. So as I mentioned before, we are seeing these multi-year variations in flow, and that's mostly in the lower sort of near terminus area, the lowermost 5 kilometers or so. So there's a velocity decrease from about 2010 to 2017, and then an increase from 2017 to present. But we are consistently seeing higher velocities in winter than in summer. So you have those darker red colors in the annual composites versus the velocities from winter that I derived. So indicating that there's sort of different processes at play here. There's still a difference, slower flow in winter, faster flow in summer. And finally, looking at Ekblaw, so it's similar to Cadogan. Once again, has undergone these patterns of multi-year variations in flow. So a velocity decrease from about 2009 to 2015, and then an increase from about 2016 to 2019. And with those higher velocities concentrated in the near terminus area. So the ITSLive data for Ekblaw Glacier was a lot noisier than the other glaciers, which you can kind of see in 2009 and 2010. But there is a difference between summer and winter flow speeds, which shows more clearly in about the 2013 to 2016 area, where you can see that it's flowing faster in the summer and further up glacier in the summer than it is in the winter. There's less of a difference when Ekblaw has these sort of elevated velocities at the terminus. You have faster flow persisting throughout the winter, but Ekblaw hasn't undergone this consistent acceleration from 2009 to 2019 like we've seen in Trinity and Wykeham. So there's different processes there. So what we can see from that data is that, again, higher velocities appear to be propagating up glacier on Trinity since about 2017 and Wykeham since about 2014 or 2015. And I'll just play this video. And this is showing the spatial extent of these glacier velocities for each winter between 2009 and 2019. So I wanted to look a little bit deeper into this. And so I extracted velocities cross glacier in 5-kilometer increments to identify kind of where the greatest changes have been observed since 2009. So just to kind of draw your attention to this video, if we're looking on the south one, which is Wykeham here, as it progresses, you can really see those darker red, the higher velocities propagating up glacier, so increasing in velocity and moving further up the glacier trunk. And then looking at Trinity, when it resets, so starting in 2009, again, you can sort of see it slowly creeping up, higher velocities, seeing further up glacier. And we're seeing that especially in the last couple of years. So here are the results of those cross sections for Wykeham Glacier. So the past figures that I was showing you were the centerline velocities, so velocities derived along that long line. But now I'm looking at these shorter cross sections of each glacier. So what this is showing, the plots are showing the percent change in velocity for these glaciers between 2009 and 2019. So again, you can see the cross sections A to A prime, B to B prime, and they correspond with the plots on the left. So we're moving up glacier as we go top to bottom. So for Wykeham, we can see that the greatest changes in velocity are occurring in the lowermost 20 kilometers or so, with percent change of between 100 and 200%. So that kind of persists in the lower, well, yeah, like 0 to 20 kilometers. And then there is still some change observed in sort of 25 kilometers and up, but it's a lot less. So the greatest changes across glacier we're seeing nearest to the terminus, sort of in the lower half of Wykeham Glacier. So if we move to Trinity Glacier, we're seeing a similar but slightly different story here. So we are seeing changes in velocity near the terminus, so increases of about 50% velocity between 2009 and 2019 in the lowermost 10 kilometers. But what's interesting with Trinity is that the biggest changes that we're seeing over this 10 or so year time period is in that 15 to 30 kilometer range. So there are changes in velocity further up glacier than we have previously seen. So this indicates, again, like we saw in that video that I showed you, the higher velocities are propagating further up glacier, engaging more of that glacier in this faster flow. So again, we would expect to see changes near the terminus where it's thinner and it's more directly influenced by both ocean and air, but we wouldn't necessarily expect to see that in these higher areas of glacier, 20 to 30 kilometers. So this indicates that there might be some different processes at play for Trinity and Wykeham, where we do see these velocities propagating up glacier. And that's something that we didn't see with, not consistently anyway, with Cadigan and Ekblaw Glacier. So to sum up, there's two patterns of flow being observed on the glaciers on the Prince of Wales Icefield that I looked at. So for Trinity and Wykeham glaciers, we've seen consistent acceleration since 2009, and the velocities are propagating up glacier, so moving up into that sort of 15 to 30 kilometer range. And in addition to that, the winter velocities are becoming more comparable to summer velocities. So there's less of a difference in the last couple of years between summer and winter flow. And then moving more north for Cadigan and Ekblaw glaciers. So there's been variable velocity since 2009. So we saw that sort of multi-year velocity decrease followed by a multi-year velocity increase. And those highest velocities were focused in the very near terminus area. And for those glaciers, velocities were still generally slower in the winter and faster in the summer. So there still was this variation between seasons. So the question then becomes, what processes are driving glacier motion for these glaciers? So there's basal sliding, where in the summer season you have more surface melt, which makes its way to the bed and acts as a lubricant to facilitate flow. Then in the winter, when there's less melt, this process stops and the glacier slows down. And then you have dynamic thinning, which I talked about earlier, where the glacier has thinned to the point where it's more buoyant, leading to faster flow, more crevassing, more calving, and it creates this cycle of thinning. So I'm looking to see if I can determine sort of which process is occurring on the Prince of Wales with these 4 glaciers, and whether or not the process that's dominating flow has changed over the last few years, and what is it influenced by? So air temperature, ocean temperature, and then looking at sort of glacier geometry like bed topography or thinning rates. So the next steps for me with my research are to identify glacier thinning rates using DEM or digital elevation models to identify thinning. So determine how much the elevation of the glacier has changed over a certain amount of time. So in past studies, thinning has been observed for Trinity and Wykeham, but I'm interested in expanding the spatial and temporal resolution to look at the thinning. So those were kind of snapshots in time, but I want to look at sort of the evolution of thinning over 2009 to 2019, sort of year to year if I can. And then also to include Cadigan and Ekblaw Glacier, which haven't really been looked at before in terms of thinning, to see if it's being observed there as well. So what this figure on the right is showing are some very preliminary results of DEM differencing using the Arctic DEM. So this is showing the change in the very near terminus area of Trinity and Wykeham glaciers between 2012 and 2017. And so what we're seeing is significant thinning at the terminus of about 5 to 6 meters per year. So over this 2012 to 2017 period, that's 25 to 30 meters of thinning potentially. So I'm interested in seeing if a similar pattern extends up glacier from this area, especially in the last couple of years when we've seen the velocity increase further up glacier, and determine whether that area is also undergoing thinning, and kind of figure out or help to figure out if that is kind of facilitating this acceleration that we're seeing. I'll also look at climate reanalysis data to determine the relative importance of changes in air temperature to glacier flow. So for example, if there was a colder summer one year, did it then result in slower flow the following winter? Unfortunately, there's very little observational data for air temperature and also for ocean temperature for this area. So it's kind of difficult to say with confidence whether or not, at this time anyway, whether or not changes in air temperature or ocean temperature are having a direct impact on glacier flow. But hopefully the climate reanalysis data will give me an idea. And then for the ocean data, this is something that other people in my group are working on collecting for this region. So that's going to be another piece of the puzzle to try and understand what processes are controlling glacier flow in this area. So thank you very much, and I'm happy to take any questions.
Merci énormément, Abigail. Thank you so much, Abigail. That was absolutely fascinating. As someone who knows nothing about glaciers and the movement of glaciers, you were there being like, and they move faster in the winter and slower in the summer, and things be happening. Et je dis juste like, attends, qu'est-ce qui se passe? Oh my God, c'est plus intéressant que prévu. So if anyone has any questions, feel free to either pop them in the chat box or raise your hand, or you may just sort of unmute yourself and speak at will if you feel comfortable doing so. We're happy to sort of support your interaction in any way that we can. Si vous avez des questions, surtout n'hésitez pas à juste comme soit lever votre main, tu peux juste l'écrire dans le chat ou tu peux activer votre microphone et le poser à voix haute si vous êtes à l'aise à faire ça. Donc, voilà.
Hi, Abigail.
Hi, Anders.
I'm sorry. I had unforeseen meetings, so I just joined very, very late in your talk, which means I can't really ask about anything you said, but I do want to ask the nasty question. When are you going to be done?
Good question, Anders. Based on when I started, I'm supposed to be, like, you mean this or the whole PhD?
The whole thing.
The whole thing? In an ideal world, next summer, but we'll see about that.
Okay.
Yeah.
In the real world?
After that.
Okay. All right. Thanks.
Yeah. I'm hoping to start writing this up very, very, very soon. I have a little bit more kind of analysis to do and processing to do, but hopefully just a week or two, and then I can start writing. And yeah, so we should chat at some point as my committee member. So
absolutely.
Yeah.
Excellent. Est-ce qu'on a d'autres questions? Excellent. Do we have any other questions? Then allow me to ask a question. Abigail, so your research is like super sort of interesting and really related to, you know, climate change, climate movement, all that fun stuff. How can we take sort of these results that you're having? Because I know you said you haven't compared them to weather patterns yet, but how do you take the results that you're having and integrate them into tangible action to demonstrate the importance of climate change, if you believe that they are pertinent to sort of demonstrating the importance of climate change?
So I guess the question is kind of like, how could I maybe take something like this to someone writing policy and be like, here's kind of changes that should be made? Is that kind of what you mean, or?
Kind of, yeah. So it's like, how do we take this sort of large theoretical research concept that scientists will understand and then like translate it into either something that activists on the ground can work with, or translate it into policy, whichever is easier for you to answer.
Yeah. So as I mentioned in one of my first slides, you know, we're seeing these changes happening quite quickly, really over the last couple decades. And outside of the ice sheets, like, it's really these small glaciers that are responding quite quickly. And if you look at contribution to sea level rise, like, that's something that affects people, maybe not us in, you know, the middle of Canada. I don't know where you are right now, Chuck, but I'm in the middle of Ontario. And so that doesn't really affect me, but it does affect a lot of people. And so sea level rise is something. And then also, like I mentioned, like icebergs, that pose a huge threat as shipping has increased in the Arctic over the last, especially 10 years. A lot of ships that maybe shouldn't be up there are up there. And so as these, if we look kind of at my little study, looking at how these glaciers have increased in their velocity and they're producing more and more ice and more melt and thinning, that's directly contributing to global sea level rise. That's directly contributing to icebergs in Canadian waters. So yeah, it kind of looks like this little niche study, but it really does have pretty direct, like, A to B impacts on people. So yeah.
Amazing. And then would you say, I guess, that the industry to sort of target related to your study's results would be sort of that shipping industry, or is there sort of another industry that also sort of needs to be targeted?
In terms of like direct impact, like who is interacting with the consequences of this glacier speeding up? Yeah, you know, that is, I would say that's probably number one right now. There's not really too many communities close to this area. The closest one is Grise Fjord, which is still several hundred kilometers away. So it's kind of difficult to make that link between like what's happening on this glacier and what's happening directly in a community. But kind of bigger picture, yeah, if you have a cruise ship up in this area and you have more icebergs, what does that mean? Or if you have a coastal community and you have contributions to sea level, what does that mean? So.
Thank you. That's my question. I guess we'll do a little bit of a last call for questions. Dernier appel pour des questions, puis après on va terminer.
That's okay. I'll just say thanks for attending, everyone. It's a good opportunity for me to kind of put my research into, kind of synthesize it and think about it in a different way and present it. So it was a good experience. Thanks for attending.
Merci énormément, Abigail. Thank you so much, Abigail. Thank you all those. Thank you everyone who has attended. As I